Okay, welcome back, everybody. Welcome back, people online. So, my pleasure to introduce Ergun Yalçın, who's going to talk to us about free actions on products of projective space. Welcome.
Thank you very much. First, I would like to thank the organizers for giving me a chance to give a talk. This will be a board talk, and I will have only one theorem, actually. But I want to first also say a few words about Fred. I met him, I think, during my PhD years, on maybe 1999. When he visited Wisconsin, I was there as a student, University of Wisconsin. And then later, I think in my last sabbatical, I live in Turkey, I work in Turkey. So in my last sabbatical about 10 years ago, I visited Rochester, gave a talk there. And he was very nice to me. He came to dinner and we talked quite a bit. And I regret that I didn't know him more than that, but I regret that. I wish I had known him more. He was a very nice person, I think. So this talk is about free actions. It's a new topic on this conference a little bit. On this workshop hasn't been mentioned much. Free actions on products of real projective spaces. There are some famous conjectures in this area too. I will try to mention some of it. I will try to give a little bit of survey, but not too much survey. It's going to be about the theorem I proved recently. So the theorem says that if you have a elementary abelian 2 group, C22, and if you have a finite dimensional free, free means I'll tell you if it means a GCW complex X homotopy equivalent to a product of real projective spaces, K-many of them with different dimensions, with trivial action on mode 2 homology. Mode 2 homology. Then there is a rank restriction on the group that R should be less than a certain number computed in terms of the dimensions. And this number depends on if Ni is even or odd, or so Mn is 0 if n is even, and if it is 1 mod 4, it is 1. It's 3 mod 4, it is 2. So this is the theorem, and this solves actually a conjecture. It settles a conjecture by Kuzik from 1983. And this conjecture, a little bit more general than I stated here. He conjectures that the same inequality holds, that the same inequality holds under the condition, just weaker condition that X is has a mod 2 cohomology product of real projective spaces. So we actually stated under the condition X is he stated as finite, but I don't think it does matter. Finite GCW complex with homology of the F2 cohomology. With trivial action on mod 2 cohomology. So this is a homotopy theoretical version of that conjecture. So for the more general version for his conjecture, I don't know how to solve it. It's still open. And I will state an algebraic conjecture at some point. And that algebraic conjecture implies actually his more general version. But this is the state. You may wonder why this 0, 1, 2. There are some examples that justifies these restrictions. First example is probably easy to construct for many of us. The quaternion group, you can think this as unit quaternions in S3. So it acts on S3 freely. This also comes from the four-dimensional real representation of Q8. By the way, free action means none of the group elements fixes anything on the space. So free action means no non-trivial element fixes any point on the space. Yeah? Yeah.
The 1983 conjecture is also with free action because it didn't write it.
Yes, sir. Same inequality if it's a finite free. So free is constant. So G acts on the homology. Yeah, induced. This induced action on cohomology, G action has to be true. Yes. Any other questions? Sorry about that. So this free action, you can extend this to some joins of these n+1 copies of S3, which will be 4m+3. Or you can take the direct sum of the representation and take the unit sphere on it. So this is a free action where inside this there is a subgroup generated by ±1, and that subgroup will act with antipodal action on this S4n+3. So Z acts as antipodal action. Let's call this a Y. Y. And if I mod out, I will get the Q8 over Z, which is C2 cross C2. I get the free C2 cross C2 action on Y over Z, which is now going to be RP 4m+3. So this is why two copies of Z2 can actually act freely on a real projective space. And this action is trivial on mod 2 cohomology. you can show it using the representation. So this action is true. So it satisfies the conditions, and it gives you an action with rank 2 group on one's real projective space. For 4m plus 1, those are easier to construct. So you can take actually C4 action on an odd sphere. By considering this as a unit sphere and complex plane. And then act by the complex number I, multiplication by complex number I. And then again, inside this, there is C2. It will act by the square of I, which is -1, so it will be antipodal action. If you mod out this action on this, you get a C2 action. This is again going to be free on the Y over C2, just Z. Let's call this Z. And this will be again an RP. So with this, you have no restriction on them. Could be odd or even, but you have a C2 action. So 1 is possible with 1, and 2 is only possible for the 4m plus 1. This shows that this upper bound is the best possible. So combining these actions, one can construct some C2 to the K cross C2 to the L. One of them is 2. Which one I choose? 2. Free action on product of RP and I. Any 2 K. 4m plus 3. So this shows that the upper bound is the best possible. You can't improve it any further. Any questions? The big conjecture in this field, I should mention that is a very long-lasting conjecture called rank conjecture. This field claims that if you G again like this, acts freely and say literally on finite or finite dimensional CW complex X homotopy equivalent to product of spheres, A many spheres, then R should be less than or equal to K. This is called rank conjecture, and it's open in this most general form. Has been around quite a long time, and many people had partial cases proved of this. Recently, there is a sharpening of this you can also try to prove that it is less than number of odd spheres, odd dimension spheres. So these odd dimension spheres, version stated by Bernard Hanke, maybe earlier by other people as well. And he also proved a very best result, I think, on this. He proved that the conjecture is true. For primes bigger than 3 times the dimension of the space. So it's equal to us. And he uses something called the tame rational homotopy theory for large primes. It's apparently possible to give a version of rational homotopy theory to prove such results. The difficulty here is we have free chain complexes algebraically, and these free chain complexes over this group ring, they have some sort of Postnikov theory, but they could have a lot of non-trivial differentials on this Postnikov theory. And because of this potential non-triviality of all these differentials, it's not that easy to analyze these free chain complexes, it seems like. Lots of people had results on this. I'm not going to give a survey, but some of the names I want to mention. Gunnar Carson has theorems to.
I just wonder where the P came from.
Oh, sorry. So this is P. This is more general. But yeah. So P is in a prime, and this is the. Gunnar Carson, there is results by Broder, Adem and Broder also. And I mentioned recent result by Hanke. We also have a result on this. We prove this conjecture for the case that average dimension of the spheres is larger, much larger than the differences between the spheres. So we have a result with my student Okutan, but Bernard's result is very general and nice. So I will say, but these are more recent results. But this is the state we are at. Still open. The results we get, like Carson's and Broder, they're for equal dimensional spheres. So when the dimensions are not equal, it's not easy to handle the differentials. Again, differentials of the spectral sequence. Seems like that's the problem. So let me say a few words about how you study such equations. So for this theorem, or for this theorem too, the main technique is to look at the search spectral sequence for the Borel construction for the group action. So take my notes, stick with the notes. So to study these free actions, I mean, you could have different methods, of course, but one of the main method is studied the Serre spectral sequence for the Borel construction. So the Borel construction has been mentioned a few times during the workshop. This is the, you take, so if X is a GCW complex, you can consider this vibration. This is, you take the universal space for G, you take the cross product with X, you model out with the G action, diagonal G action. This, you can send this to any orbits on the both sides. So if you send it to G orbits, you get BG here, and your fibers are X. This is a Borel construction. Now there's a, for every vibration, you have a Serre spectral sequence. So you can look at the Serre spectral sequence for this. But the key thing is when the action is free, you can say that this total space actually homotopy equivalent to the orbit space. Because of this, and because we assume that X is finite dimensional, total space is finite dimensional cohomology. So this is the key abstraction for constructing free group actions. You will have a finite dimensional cohomology on the orbit space, on the total space. So the Borel spectral sequence, Serre spectral sequence for the Borel construction is of this form. It has a two-page A space. I'll keep any coefficients R, converges the total space, which has the cohomology of this. This is the main spectral sequence we look at. Now, this spectral sequence, when G is elementary abelian group, will have a lot of infinite to many non-trivial cohomology on horizontal lines. This is finite, but the result has to be finite. So differential has to be quite special to make this, to converge to a finite dimensional cohomology. Yes. So how do you avoid this? So if R is F2, and the action, we assume that, so for this, we assume the action is trivial. The induced G action is trivial. Homology is trivial. So this is a very special case. So in this case, we have no actual non-trivial action. We don't have to deal with local coefficients. So we have just a product. Actually, I would like to write it as a star. It's a direct sum of all these possible. And this turned out to be algebra isomorphism. So this is going to be an F2 algebra isomorphism. So you have a cup product structure on this and gives you a product structure on E2 page. That product structure respects the differentials. So spectral sequence has a product structure. So if you observations about this, we have very kind of easy cohomology. You can calculate so one thing you observe that when X is this product of spheres, product of real projective spaces, this thing, finite theorem, just polynomial algebra. Oh, sorry. Let me go with the BG first. So this is just the polynomial algebra. Number of copies of C2 as the number of generators. For the RPN, similarly, you can say that this is going to be polynomial algebra mod out of the relations. So we have a spectral sequence, we have the cohomology. We can look at what kind of differentials. Because the action is trivial, we can identify this as cohomology of X. And this cohomology of the BG. And then you have the generators Ti at the dimension 1. So these have all dimension 1. So first differential B2, it's H2. I call them alpha I. These are the image of differentials. And they sit in the H2. So they can be considered as two-dimensional polynomials. So these are quadratic polynomials in these variables. So you have k many polynomials in r many variables. Now we haven't used free action yet. So with the free action, what you know is that everything has to go. So at the end, you should have a finite dimensional E infinity page. So that's the restriction. But that restriction could be also applied to the subgroups, because you have a nice naturality with subgroups. You can go down to any subgroup, and you will have a associated spectral sequence for a subgroup. And the differential here, the image of the D2, will go to the restriction. In the group cohomology, you have a map from a cohomology of the big group to the subgroup, cohomology of the subgroup, called restriction map. So in that case, you'll have the restriction of this to a subgroup. And using this observation and restricting to cyclic subgroups, it's being proved that these quadratic polynomials have no common zero when they're considered as polynomials. So these are in F2, not over K, but in F2, they're considered as polynomials. Degree 2 polynomials. And this is because if you add a common zero, you could use those coefficients of the 0 point to build a cyclic subgroup, and you can restrict to that cyclic subgroup. You'll get a 0, but having this differential 0 makes the associated spectral sequence collapse, and the collapsing will make it infinite dimensional. So it will not be finite dimensional. So because of that, these things have no common zero. So this already tells us by a result that R less than 2K. This is a result that follows from polynomials with degree n, homogeneous polynomials of degree n. If you have K of them, if they have no common zero, the number of variables has to be less than nk. There's a result like that. And so we get the 2K already from this. But this is, as you see, doesn't see if the dimensions are 1 mod 4 or not. It's a general result. So what Kuzik's observed, this is Kuzik's observation. He sees that if ni's are 1 mod 4, the associated, by the way, I call these K invariants. So these are usually called K invariants of the action. The associated K invariant has the property that C0 power of it, first in this case, because it's only polynomial, degree 2 polynomial, lies inside the ideal generated by the other K invariants. So this follows from a very easy argument of powers goes to 0, so you have to have this. So it actually follows from the fact that C0 powers this is going to be Ti squared. And by a theorem, couldn't find the exact reference for it, but it appears in Hatcher's book. If you take the C0 power on the left-hand side, the V3 of that hits the C0 power of the right-hand side. So there is a commutativity of the C0 powers.
More generally than that, the Steenrod operations are completely in the spectral sequence, and the excess condition not satisfied. So you know that that has to die by the time it gets to E infinity, and you can use the fact that the excess condition holds at infinity to compute differentials.
I guess, but this is just Kuzik's observation that D3 has to be this, but by calculating the powers, he sees that this is 0 in E3 H, and because of that, it has to hit by something here. So that's how you conclude this, that there have to be something in here, E11. And because it hits it, you can show that SQ1 alpha I can be written as a sum of some linear polynomials times. So this is his argument. He combines this with a result by Serre. It says that if you have a polynomials like this, have no common zero, and they generate a C0 closed ideal, then this R less than 2K can be improved to R less than K. So this is a result by Serre about still not closed ideals having no common zero in F2. So you can see now how like still-not operations become part of the picture, and what Kuziks is able to prove with this in the same paper, the conjecture is true if all the dimensions are 1 mod 4. So if you have nothing, so his result on the same paper is that Ni, all of them is 1 mod 4, then this is true. So when do I finish? Because I started a little bit late. Huh? I don't know. Depends on how much I have. I can use it. I can use the whole afternoon. You don't want me to do that. Okay. I started late though. I thought. Okay, so okay, so let me say a few things about how to continue. So you can see that this condition was a necessary condition because basically he or other people who worked on this couldn't handle the fact that some ideal is partially still-not close. By this I mean that some of the SQ1s are inside the ideal, but this is not true for all of them. So this brings a conjecture. I saw this in paper by Allday. It's an algebraic conjecture. It will be interesting to solve this. If you have quadratic polynomials in F2 are such that they have no common zero. And then second is that SQ1 of some of these elements is in the ideal. Then we want to say that partialness gives you a slightly improved bond. This is an open question. This is an open problem. And this implies the F2 version of Kuziks conjecture. But I don't know how this can be proved either. It's an open question. We studied these kind of elementary abelian group extension by elementary abelian group extensions with Jonathan Pakianathan, who's going to come tomorrow, I think. And the still-not operations gives a very nice internal structure on this kind of extensions. And we had issues like diagonalizable, triangulizable. We built a two restricted Lie algebra out of these. So these can be very interesting to study. Just the quadratic polynomials with some still-not power operations. So what is the new idea for this theorem? Maybe put you can guess that I am insistent that X is homotopy equivalent. So somewhere I will use integral cohomology. So new input is using integral cohomology, using the for our spectral sequence in coefficients. Now there are a few difficulties that comes with it. One of them is calculating cohomology. There are some already existing calculations. For example, for elementary abelian 2 group, this is known. There are some, it's actually almost a F2 algebra with some generators. Some relations where all these generators have actually torsion 2. And there is some relation which is very ugly to write, but something involving some of the products. This is from a paper by Benson and Carson. I'm writing it from. And I think it might have been done before them, but they give a full proof in their paper where they study the integral cohomology of X special 2 groups. So they need this calculation. So you take all the J's in the intersection. Now you have two sums. Now you have the symmetric difference. Add the J. And then you have another summand. I'm not writing this so that you can just give you an idea. This is the J, and this is for J in difference of J minus I. So these generators actually have degree order of I plus 1, and their mode 2 reduction is actually something familiar. They will be the Bochsteiner product of TIs. They're kind of easy to know what they are, but this relation seems to be a little bit tricky to write. So this is BG. There's a similar calculation for RPN, product of RPNs. I think it might be well known also, but I'm not going to write it. But you have to calculate the integral cohomology. And then, because you do know the mode 2 cohomology, you have to combine these two cohomologies in the integral spectral sequence. So that's what we did. Take 5 more minutes. Finish very fast. So we compare two spectral sequences. One is F2 coefficient one, and then the other is the 2-page. This is actually all the pages I will write the same way. This is F2. So you have generators here, TI. We knew that they go to the K invariance, and the action here was trivial on the cohomology. So this was just the cohomology of X and this was just the cohomology of BG, and have two coefficients. It's a polynomial algebra. This one is a truncated polynomial algebra, and this alpha is had no common zero. The trick was the Stirnod powers goes to the Stirnod power, but they gave something still not very easy to figure out. Algebraically, we had a problem we couldn't solve. So the idea here is, why not look at the integral one? And maybe we'll have a little bit better idea what happens here. So in the integral one, set 2 to the r, you have some ui's and u12 and so on. So you have these generators, but there's nothing here. And then this line, there's similar calculation with generator, I call them SI. So there will be similar ones with SI, and they will be here. And there will be still SIJs, and so on. It turns out that because RPN, when n is odd, may have a z at the top dimension, you also have some generators, we call them VI, and the generators are in the dimension Ni. This is only when Ni is odd. And those are the integral ones. These are two torsion classes. So the idea is to analyze with the non-trivial G action what will happen to these things and how they will hit things. So first observation we made was we saw that this is Bochstein 0, which is the connecting homomorphism from the Z2 to cohomology of Z. So we have this short exact sequence. So that gives you either connecting homomorphism to the next one. We call this integral Bochstein. So the integral Bochstein actually hits this, and then you can show that the tree of this, there should be also integral Bochstein. So there's a commutativity similar to the Stirnod powers for the integral Bochstein. And by using this, you can prove the results. One thing we proved that if the G action on the integral cohomology is trivial, then this Bochstein of this alpha i's are 0, which actually implies very easy argument that these are just the squares of some things. So they have to be a square polynomial. If the G action is trivial, this will be true for all Ni 1 mod 4. So instead of saying that the Stirnod powers falls in the ideal, you say something stronger, that their Bochstein is 0, integral Bochstein, and that forces that polynomial to be a square polynomial. The second observation, which is a little bit harder to prove, and in more general case, which possibly non-trivial, with the same condition, then you can prove that this Bochstein is no longer 0, but Stirnod powers of these alpha i's are in the ideal generated by alpha I. So this is what I said, the diagonalizable situation, not in the ideal generated by all, but itself. This also gives you something straightforward that is product of two one-dimensional classes. This you can prove by easy arguments. But the proof of this and this of it involves the spectral sequence. So if you have these stronger conclusions about the K invariance for the Ni equals to 1 mod 4, you can easily modify the argument for the rank, and you can get that R should be less than equal to the sum of these MNIs. Because these things will be almost linear, they have a hyperplane as kernels, so you can easily revise the argument to prove this inequality. Once you have such a strong conclusion about the K invariance. So this is how the proof goes. Sorry, I had to extend my time, but this is all.
So thank you. It was very nice. I was noticing, well, it's quite clear that